in this course we are going to talk about design of mixed signal current mode control in a buck converter with some simulation, MATLAB simulation case studies. So, here we will first revisit the mixed signal current mode control, we will discuss the design of mixed signal current mode control, we will take some design case study with our realistic hardware parameter values and we will make some MATLAB simulation case studies. Then if we consider this mixed signal peak current mode control, we have discussed multiple time week 3 as well as we made MATLAB simulation in week 3. Here we are talking about inductor, capacitor, input voltage, output voltage, switching frequency. This thing also we have discussed multiple times about our hardware prototype and their power stage parameters. Now, if we go for implementing, what we are using our DAC, here we have a V sense, that means our V sense has that is your IL, we have considered some Kc which will give V sense, and this Kc we have considered 0.01 volt per ampere. And if we take the loop transfer function, here also we have used a feedback gain due to the resistive divider. So, this Kf is 0.27 that we found, and and we also got some gain here when there is a binary transformation, and I will discuss about this DAC. So, I mean if you write the loop transfer function, the effective loop transfer function. So, Kf is the feedback gain due to the voltage resistive divider, 1 by k ADC is the DAC gain and which is 1 by 4, and then we are getting 1 by Kc which is like, because Kc is how much? Kc is 0.01 volt per ampere, and then this is our traditional current to the control current to inductor current transfer function, and this is the controller that we are going to use. So, if you write the loop transfer function here, then in this loop transfer function, if we want to achieve, in fact we should have additional e to the power minus s tau d, that term will come here in the loop transfer function because it is part of the loop, and then the target bandwidth is Fs by 8. Then if we draw the Bode plot, you will get phase margin slightly less than 95 degree, because here there will be an additional drop due to the crossover frequency into tau d, and that phase will also come in degree. And since our tau d is, we are getting like a 0.35 microsecond, and what is our crossover frequency? It is 2 pi FSW by what is FSW by 8, and what is FSW? 2 pi by T into 8, that means into 8, that means 80, I would say it is 80. So, then what is omega c into tau d? It will be, T is 5 microsecond, so it will be 2 pi divided by 0.35, divided by 8 into 5, 40. Okay. So, this term is quite small, that means we can consider to be this is very small, that omega c into tau d. So, as a result the phase contribution will be very negligible, insignificant. And if we design the peak current mode control for this gain, we found that Kp to be coming to 4.64 and Ki to be 0.4, this is discrete time integral gain, to achieve a bandwidth of Fs by 8. And this is what we are going to implement. First we made simulation, and we will also show hardware experimental result as well for the same configuration, same proportional gain, same integral gain, and now, and this is what we have made the FPGA. We have up to this point we have in the FPGA, then again this comparator output to this block, it is the part of this we kept inside the FPGA digital implementation. Now, digital PI controller, we have used this 4 point, what we got 4.764, and this is Ki equal to 0.4. So, this corresponds to Kp equal to 4.64 and Ki to be 0.4, and this is again we are getting Now, we want to show the load step up transient. Here input voltage is 3.3, output is 1 volt, and we are making a load transient by changing this resistance, and we know that there is a continuous resistance which is RC, and there is a switch resistance which there is a switch, and this gate signal we are using like a gate signal, that is our Q load. And what is this RSW? This is nothing but this, and RC is nothing but this. So, we are making, so if you turn on the Q load, make it high, it will make a load step up transient. If you make it 0, it will be load step down transient. So, this is a load step up transient, and that we are making, it is almost like a 3 ampere load step, and since it is a current mode control and we are making 1/8 of the switching frequency, because if you try to go beyond 1/8, then there will be a model validity issue which we have discussed in our earlier NPTEL course. And current mode control is a sluggish because it looks almost like a fast order system, and you can see from the response for both step up and step down, the response changes very nicely, but after that it takes a lot of time to come back. And if you go for reference step transient, it is very fast, and the same controller gain. What we are doing here, we have used only the continuous resistance here, that means we are not changing any now, that means this is the configuration RC, and we are making changing this voltage, that means we are changing this output voltage by changing the reference comment, only 0.1 volt. This response is pretty fast, and we can see the step down transient response, and this is, I would say, it's a nicely designed because we made for FSW by 8. And the load step up transient, if we take a higher input voltage and higher output voltage, then the step size will be, in this case the load step size will be almost like a more than 5 ampere, or here it is like a 5.4 ampere load step size, because we have increased the voltage by 0.8, or it is 1 volt, it is now 0.8 volt. So, you can see the response is bit sluggish because of the first order nature of the current mode control. The step down response is also bit sluggish, and if you see the reference transient performance for 13.5 for higher input voltage, these are the response, this is looks fast. So, we can get reasonably fast transient response, and all cases we are using Kp to be 4.64, and discrete time integral gain, that is KID, is 0.4, and for KPD and Kp continuous time and discrete time, they are same. And in the subsequent lecture, we are going to show hardware case study. So, in summary, we have discussed mixed signal current mode control design aspect, then we have considered some MATLAB simulation case study for the design of mixed signal current mode control, and in the subsequent lecture, we are going to show the hardware experimental result related to the similar, the hardware configuration. That is it for today. Thank you very much.